Celsius. It's a little chilly.
Give it a couple minutes as people are still filtering in.
Yeah, I think the stream is live.
Okay, people have joining us slowed, so we'll get started. Good morning, everyone. Welcome to the third day of Planks. I'm very excited to be joined today with these two great events this morning. So we're starting off with our CERN talk. I'd like to give a warm welcome to those who've joined from the public. Welcome to Planks. This 3-day symposium is coming to an end. It's been great, but Planks happens every year and is hosted by a different group of students at a university each year. It's organised overall by IAPS, the International Association of Physics Students, supported by the Institute of Physics as part of their programme of activities for the physics student community for apprentices, trainees throughout the year. Planks is just one event, but the IOP and IAPS organise and support students to organise other great events, bringing people together, providing opportunities to take part in competitions, discover physics, and enhance your personal development. So you can join via the website. It's cheap and definitely worth it if you get events like this. And you can have a look at what else is taking place around the UK and Ireland by visiting the IOP website and the IOP student community pages. You can definitely think about potentially getting involved with running stuff like Planks yourselves. And I'm sure Julian would love to hear from you guys if you're interested in hosting this competition or others next year. So do send him a message and let him know. It's been real great. I definitely recommend people host this event. I've had a lot of fun, and I'm sure you would too. So just some housekeeping first. If you have joined, please stay with your webcam off and your microphone muted. You can contribute your thoughts and questions in the chat. Myself and Joe will be monitoring the chat and then running the Q&A session afterwards. Yeah, if something speaks to you, feel free to express it in the chat and we'll try to pick it up. Please bear in mind that we have a lot of people joining us today, so if we don't get to your question, it's not personal. There might just be a lot of questions. So with that, I'm going to introduce our two speakers today. Firstly, we have Dr. April Critland. She is a postdoctoral researcher with Swansea University and stationed at CERN in Geneva. She completed her PhD in the development of planar penning trap for quantum applications with electrons at Sussex University in 2018, after which she moved to Geneva to join the Alpha collaboration at CERN. Her research is focused on studying the fundamental properties of antihydrogen by designing and building new penning traps, which incorporate fluorescence detectors at cryogenic temperatures. She's passionate about increasing diversity in physics through a myriad of outreach channels, including talks to schools, tours of CERN's facilities, and contributions to YouTube videos. In 2020, she co-founded and organized the first early career conference in trapped ions, which aims to provide a supportive atmosphere for early career researchers to present their research to an international audience of their peers. We also have with us Adam Powell. Adam is a PhD student with the University of Calgary and based at CERN. Adam joined the Alpha experiment as a master's student with Swansea University in 2018, working on electrostatic manipulation of positron bunches. In 2019, his research focus shifted to in situ magnetron. My brain is not working this morning. Magnetometry. We'll go with that. I'm sure Adam will tell us a bit more. For Alpha, using electron plasmas, penning trap development, and microwave spectroscopy of antihydrogen. He's been involved extensively in outreach through the Institute of Physics, the British Science Association, and CERN. As an active member of the Institute of Physics Committee for Wales, he has a passion for increasing physics participation across the nation and engaging the physics community with the wider population. Adam was the organizer of the first All Wales Physics Student Conference in 2018 and co-organizer of the Conference for Physics and Astronomy Students UK in 2019 in Swansea. So with that, I'm going to hand you over to our two fabulous speakers today, and you're in for a great talk. So over to you guys.
Thank you very much. Thank you for the lovely introduction. And thank you for the organisers for setting up this weekend and inviting us to join you. So as you can see, we're going to focus on antimatter, and we're going to focus on what we actually do at CERN with the Alpha experiment. But if you take a look at just our first slide, if you turn up at CERN, this is what you'll see outside of the gates. So this is the globe. And so there's all sorts of different public outreach that goes on here if and when you get the chance to travel later. And if you fly into Geneva, you can spot this building from the plane, so you know where you're heading. Okay, here we go. So what we're going to do is we're going to split this up a little bit. So first of all, Adam will take us through what is antimatter before we go any further. And we're well aware that this is a Sunday morning and everyone's a little sleepy. So there'll be no mathematics, there'll be nothing to worry about. It's okay. And then we'll go through what is CERN itself. Hopefully you've already heard of CERN, but you might not know any of the details. And rather unusually for this kind of talk, we will take you for a walk around the building. And then we will introduce you to our actual experiment and take you for a walk around our experimental zone. This part you will never normally see if you come and visit CERN, because the public is not allowed in this area. So you're getting a prize view here. And then finally, if you're interested in coming and working at CERN, or you're interested in joining us within the Alpha collaboration, we'll give you a couple of slides on how you can do that and the different routes in. So, slides changing a little slowly. So we've already gone through a little bit about who we are. So if you have questions that are really PhD related, obviously Adam is doing that right now, but it hasn't been that long since I did mine. So we can help you with those, and we can also give you a little bit of information career-wise on what it's like to be a researcher. So what I'll do now is I'll hand over to Adam, and he'll take us through what is antimatter.
Good morning, everyone. Thanks for having us. It's always exciting to talk about CERN and to talk about our research, even if it is a Sunday morning. So I want to start off with the fact that antimatter gets some bad press. I mean, it's either famous for blowing up the Vatican in fiction novels, or if you just Google antimatter, you get some interesting results, usually focused around bombs and how we destroy the Earth. There are even some interesting articles that come out that claim we unleash hell on Earth. And I know you're thinking that this must be some small tin shed operation that likes to exaggerate what scientists do, but actually this was an article from the Mail Online. They did get one thing right, however, it's that we do manage to trap and study antimatter. That's what we do. That's what this entire facility at CERN is about. So, what is antimatter? The physicists in the crowd will know this man, Paul Dirac, famous for attempting to unify quantum mechanics and special relativity. This was a hot topic in the early 20th century, and we wanted to know how to describe electrons when they moved close to the speed of light. His famous equation, which you can see on the right here, on the floor of Westminster Abbey, just near Newton, gave two possible solutions for the motion of these electrons near the speed of light. One that was an electron moving with positive energy, and one that was an electron that had some negative energy. Obviously, negative energy doesn't exist. So Dirac, being the genius that he is, said, well, what if actually this negative energy electron is actually a positively charged electron that has positive energy? And so the solution to his equation directly gave us our first understanding of what this antimatter should be. So exactly like an electron, but with an opposite electric charge. That's the crux of what we're talking about here today. So where does that fit in the timeline of the universe? Well, we've got here the Big Bang, and right the way through to today, the LHC focuses on events kind of in this time frame, which is the 0.1 of a nanosecond after the Big Bang. But way before that, all of the antimatter in the universe seemed to disappear. All models we have for the Big Bang suggest that matter and antimatter were created in equal amounts. But as you can tell by the fact that I'm talking to you on a computer that's made of matter, sat on a chair made of matter, we live in a universe that's heavily one-sided. So we wonder about this missing antimatter. The standard model of physics doesn't account for it. We have no current accepted theories that suggest this asymmetry should exist. And so this is a big puzzle in physics, the whole motivation for this and much more research. The thing that ALPHA tries to do is to study antihydrogen, antihydrogen being the simplest anti-atom available, and April will talk much more about this later. Why do we do this? Well, because hydrogen and antihydrogen should have the same atomic energy levels. If we see a difference in these two things by directly comparing them, maybe we can come up with an answer for why we live in a matter-dominated universe.
Okay, so we've got the introduction to what is antimatter, and now we need to talk about, well, what is CERN, really? So you might have heard of the name, but you might not really know where it is or what it does. So the actual acronym for CERN comes from the French, which I've put there for you. And it was founded in 1954, so it's been going a fair while now, and it was actually one of the first joint things after the Second World War that Europe did together. So CERN focuses really on looking at the fundamental particles that make up everything around us. And what we want to do is we want to try and understand all the forces of nature to a great detail and how they all fit together. And this, it says here, you know, that CERN's often referred to the European Laboratory for Particle Physics, but it's also the UK National Particle physics laboratory. So the UK puts funding into CERN, and we use this as our national laboratory for physics. So where is it? So I've added Swansea because we're both related to Swansea, so you can see where we are from there. But you'll see where CERN is just sticks out on the little bit of Switzerland that sticks into France. And what it actually does is it really sits on the French-Swiss border. So we'll see that in a second. Now, these are all the different member states of CERN. So all of these states put in a certain amount of money each year. A certain amount of staff and students from all of these states come to CERN to work, to contribute. And this actually needs updating. There's 2 more states have joined as associate members. There's Estonia and Croatia. So Croatia joined in 2019 and Estonia joined just this year. So this is still a very active community. And 3 of these associate members will go on to become full members soon. So here we see the full ring of the Large Hadron Collider. So this is probably what most people think of when they think of CERN. And this gives you an idea of the scale. So this is 27 kilometers round. You can see the dotted white line there that shows you where the French-Swiss border is. So there's multiple points that the LHC actually crosses the border from Switzerland into France and back again. And what you can see is there's 4 big experiments that sit around this ring. So you can see LHCb, you can see ATLAS, you can see ALICE, and you can see CMS. So these are 4 big experiments that sit on the LHC itself, but there are many, many more experiments that are a part of CERN, and we'll look at a few bits of it as we go. My slide changing is very slow. Here we go. So if we have a quick look at ATLAS, for instance, ATLAS is huge, okay? You can see the guy standing at the very, very front to give you a perspective of this picture. So ATLAS is as big as a 5-story building. Part of the reason why these experiments are so large is that there's so much energy in the particles as they go around the ring that they travel a long distance. So what they want to do is try and detect as many of these particles as possible. So you need a really big detector to try and catch as many as you can. And one other that we're going to look at is CMS. And CMS, although the C stands for compact, it might be smaller than ATLAS. It's certainly not lighter than ATLAS. So you can see here, this is actually heavier than the Eiffel Tower, but it's not just thinking about it as heavier than the Eiffel Tower. This has got about the weight of 30 jumbo jets, or if you really have an idea about elephants, is about 2,500 elephants is the weight of this thing. So it might be compact for a particle detector, but it's certainly not light. And as you can see, we've got an immense amount of electronics that are needed for these things. So this takes a lot of people to put these big experiments together. So these experiments like ATLAS, LHCb, they have over 1,000 people working just on that experiment. Okay. So these really are some of the bigger ones. But that's not all that CERN is. So you can see we've got the LHC ring with ATLAS and CMS on that we've already looked at. But the CERN complex is much more than that. You need quite a few accelerators before you get up to the LHC. So if we have a look in the bottom corner here, you'll see something called LINAC 4. And what we're going to do is you're just going to follow this route around. So LINAC 4 starts with negative hydrogen ions, and I'll talk a little bit about that in a second. But it goes into this booster here, where we get our protons. And then it gets accelerated again in the next one where it says PS. So you'll see PS stands for proton synchrotron. And then from there, you follow this line up, you'll see it goes into the SPS, which is the super proton synchrotron. And then from here, there are two exits. So there's one exit that goes towards ALICE, and then there's one exit that goes towards LHCb. So what happens is the SPS injects protons into the LHC in two directions. So they go into the LHC in both directions. They accelerate them as much as possible in the LHC, and then they control the beams so that at each of these 4 locations of ATLAS, LHCb, CMS, and ALICE, these two beams cross. And that's how they collide these protons together. So at each of the locations of the big experiments, we get these proton collisions. And then what the big experiments are looking at is, well, what is the fallout from this? What particles are given off? What are their energies? Which way do they go? And then you try and reconstruct, basically go backwards, the actual collision itself to better understand how these particles interact with each other and what kind of energies that we were seeing shortly after the Big Bang. So this is all about the LHC, that's fine, but that's not what we work on. In fact, if the LHC was running, we wouldn't be bothered. What we care about is those injector systems that are at the beginning. So if we zoom in, so see here's my LINAC 4, and you'll see it says 2020, because this has just had a new upgrade. It used to be LINAC 2. So now we're up to LINAC 4. So now we actually have a negative hydrogen ion source instead of just a simple hydrogen source. So if you follow the line here, we get to the booster. You can see we strip off at this point here, we strip off the extra electrons that are part of this hydrogen ion. And this is where we get the protons ready to go into this booster. So you see the booster's been around a while, but it's not as old as the PS. If you come into the PS, you'll see, let's change too fast now. You'll see the PS was built in 1959. So this has been here from the beginning. So you'll see from the PS, we feed it up and we get to a point where you see a proton, changes to an antiproton. And what we're going to do now is we're going to have a look at what happens here and what happens inside this building that contains these two parts here. And Adam's going to take us through that now.
Okay, so April's given you a nice overview of CERN generally, and I'm going to be selfish and just talk about antimatter because that's what I'm interested in. So I'm actually sat in the Alpha control room in the antimatter factory. This is our view from outside, and yes, it is always that sunny. April laughs. As you can see, the antimatter factory has two weird symbols kind of on the sides here. This stands for the AD, which is the antiproton decelerator, and ELENA, the extra low energy antiproton ring. So what does that mean? April talked about the PS, the proton synchrotron. So that gives us high energy protons. They come in along this beamline and hit into a metal block. By hitting these protons into at high energy into a block of iridium, we produce antiprotons. These are then filtered out using a big magnet and brought towards our experiments. So you'll notice I said antiproton decelerator. CERN is famous for making things go very fast and then hit into each other. That's the opposite of what we do. We're interested in precision measurements. So we want low energy particles. We want to be able to stop these antiprotons. We want to be able to combine them with other things and study them very precisely. So we are actually in a decelerator facility. So the antiprotons will circulate around this decelerator, and we'll take a look at that in a second. Then they'll move into ELENA, which is new this year, just being commissioned, and then off into the various different experiments here that will use these antiprotons to try and understand this matter-antimatter asymmetry I talked about earlier. So now we're going to rely on the wonders of the internet to see if we can get a video of our tour working. So I'm going to start at this point with the star. April and I walked around the facility a couple of days ago. So this is how you access an accelerator at CERN. Looks very high tech. There's a bunch of keys you can see here. Every person who enters the during an operational period takes one of these. Your retina then scanned as you walk through this door and into the experiments, into the accelerator. Since CERN is on a shutdown at the moment, we can bypass the main security door and start where a standard CERN visit would start. So I'm going to walk against the direction of the antiproton flow, and we're going to talk about the magnetic fields that are required to keep particles in a beamline. So you'll see this red structure. This is a magnet. There are 4 sets of coils here. This produces a quadrupolar magnetic field, and this is used to squeeze and compress our antiproton bunch. We then come to a blue structure. This has 2 sets of metal wires. This produces a dipolar field. So this is used to push our antiprotons around in a circle. Particles like to move in a straight line unless you apply an external field to them. So we're applying magnetic fields to shape and move the particles where we want them, ready to be decelerated. This requires a lot of current, so you can see here some quite chunky power cables, just for your interest. So now we're going to move on to what actually does the cooling and deceleration of these antiprotons. I'll use cooling interchangeably with low energy. Cold antiprotons are low energy antiprotons. So the AD uses a number of different cooling techniques. This is by far the most interesting to look at. This is an electron cooler. So what this does, it emits electrons into our beamline to sit in a high magnetic field. Electrons that sit in a high magnetic field rotate and emit synchrotron radiation, and they get cold, they get low energy. We then hold those on top of our antiproton beam and absorb some of that energy. Think of it the same way as holding a cold can of Coke in your hand on a hot day. The energy from your hand goes into the cold can. We're going to move over to an interesting part of the beamline here, where the beam enters the accelerator and also exits it after doing its multiple cycles around the circuit. So this one's kind of tricky to see, but in the background there is where the target lives in a separate building. It comes through and joins the main beamline of the accelerator here, and then there's a split. So this split is where the now low energy antiprotons are siphoned off and through this wall into a laner, which we'll see in a second. So the beam, if we ever have a problem in the facility, we can dump the beam to a beam stopper on this side, which is surrounded by lead to absorb the radiation. So now we'll move directly up above where the last video was took. We're moving outside of the concrete bunker that we were previously in for radiation shielding. The laner is lower energy, so there's less of a radiation risk. You'll see again an array of magnets here. The orange ones are this time the 4 sets of coils, the quadrupoles. The blue ones are still the ones that steer us around that circle. Interesting shape here. This silver object is an RF cavity, so that's a radio frequency cavity. This applies an electric potential to the antiproton bunch and decelerates it. Think of it like trying to run up a hill. Your energy is being drained and absorbed. We've got another blue electron cooler here. So this again, think of it that can of Coke absorbing the energy from your hand. And then we're moving around the outside of the beam and the antiproton bunches are then filtered off by this silver object and moved to the various experiments around the facility. So yeah, that's our little overview of the facility. Again, I'll just recap some of the things we talked about. Our high energy protons produce antiprotons from an irradiant target. We then decelerate them and eject them at 1,000 times lower in energy. We then move them into our second decelerator, and then they lose a factor of 50 energy and are then moved on to the experiments where we can do some interesting physics with them. There are a number of experiments around the facility. Alpha is the focus of today, and April will shortly talk about that a bit more. But we do have some company in the hall here. BASE do some interesting measurements just using antiprotons, and they can hold on to these antiprotons for years. They're limited by just how good a vacuum they can produce in their experiment. So really interesting things there. And the other guys also make anti-hydrogen in different ways to Alpha, but all equally interesting and worth a look if we inspire you today. So with that, I'll hand over to April.
Great, thanks. So we've already said that Alpha works with anti-hydrogen, but it's always best just to have a quick overview and a quick reminder of what we're talking about. So we know normal hydrogen is the simplest element on your periodic table. So it's just made up of one proton and one electron. And the great thing about hydrogen is it's really well understood. The theory is there, and there are a multitude of experiments that really understand hydrogen to a high precision. So it makes a great comparison atom. So what we want to do then is make anti-hydrogen, so we can make those comparisons and have a look. Is anti-hydrogen any different to hydrogen itself? So to make anti-hydrogen, we need those antiprotons, and we've just seen how we get those. And we need some positrons. So what we're going to do is we're going to have a look at how do we make the positrons and how do we bring the antiprotons and the positrons together. So this is just a simple sketch overview of Alpha. So you can see on the left here, we get those antiprotons from the AD, and then this year through ELENA, so even slower. And we have this green thing here called the catching trap. So what we do is we catch those antiprotons in here, and we hold on to them until we're ready. We catch about 70% of what we're sent, and we can be sent bunches every 2 minutes over what was previously an 8-hour schedule, but maybe with ELENA coming online, this might end up being 24 hours a day. And then if I jump over to the right-hand side, we have this positron source, which is made of radioactive sodium-22. So this gives off positrons. Interestingly enough, so does the banana in your kitchen, but this gives off way more positrons. And what we do is we accumulate them in this long yellow bit here. So we accumulate those positrons. Takes about 70 seconds to get enough positrons to work with. And then we move both the positrons and the antiprotons into this atom trap in the center. So you'll notice everything is cylinders here. And there's a very good reason for that. So let's have a look, first of all, about how we control these things. Because I've already said we catch antiprotons. And what does that really mean? How do you catch something like this? How do you hold on to it? So what we use are penning traps. So a penning trap has two parts. It has a static electric field. So it creates a well, which charged particles can sit in and bounce back and forth inside the well. But that's not enough just to hold a charged particle, because it could escape from the top. And it could also escape from the side. So what you do to your electric field is you add a static magnetic field. And of course, we all know charged particle in a magnetic field wants to go round. You've got the right-hand rule that tells you which way it's going to go. So if you combine these two things, a static electric field and a static magnetic field, what the particle actually does is a motion like this. So this is a superposition of 3 motions. This is 3 harmonic oscillators. So you've got that axial, that green one, which is the bounce up and down, which is caused by the electric field. You've got the really small circular motion, the cyclotron, which is caused by the magnetic field. And then you've got this long, slow drift around called the magnetron motion. And this is caused by the combination of both the electric and the magnetic fields. So this is how we actually hold charged particles. Remember, our antiproton has a charge, our positron has a charge. So we can hold both of these using a penny trap. And that's what sits inside those cylindrical structures with the magnet on the outside. So what we're going to do is we're going to open up that central atom trap and have a look inside. So we've got 3 layers of blue things on the outside here. That's our silicon vertex detector. And at the end of this video, you'll see how that works, because there's no point having antimatter if you don't know you've got it. On the inside of this, you'll see there's some magnets. So these magnets here are actually used to hold the antihydrogen once we've made it. So the octopole there holds the antihydrogen radially, and these mirror coils on either end hold the antihydrogen axially, so they stop it slipping out the ends. And this works because antihydrogen has a magnetic moment, so it responds to a magnetic field, even though once you've made it, it doesn't have a charge. So if we look inside this, there's our penny trap. You see, these are electrodes, they're gold-plated electrodes, and this is where we apply the electric fields. And Adam actually has one in his hand right now, so you can see the general size of this section in the middle. It's pretty small. So these are our electric fields. So we've got our antiprotons on one side, we've got our positrons on the other, and we just slowly merge these 2 things together. And this is where we make our antihydrogen. So we make this with 3-body recombination. So we need 2 positrons for 1 antiproton. So one of the positrons gets trapped by the antiproton, and the other positron carries away all the excess energy. Now we've got our antihydrogen. And those magnets that I just showed you, that octopole and those mirrors, they create this kind of like bathtub potential that you can see at the bottom here. And this is what keeps our antihydrogen in this space. Now, this is only going to keep the antihydrogen until we let the magnets go. And it hits on the side of our trap, and it causes a response from our silicon vertex detector. So these tracks, you can trace them back where it's hit the vertex detector and see where the annihilation actually happened. So we can look at this in a bit better detail with this GIF. So what's happening here is when the annihilation happens, this is giving off pions and some gamma rays. And it's the pions that we're looking at. That's what we're tracking with our silicon vertex detector. And because we've got these 3 layers, we get at least 3 hits on the way out of these pions so that we can track them back to the center. If when we track them back, it doesn't make sense, maybe it's not really happened inside the trap. This could be caused by a cosmic ray coming in from outside. So we do have some background to worry about there. So to give you some numbers, some ideas of what we're talking about, if we have about 100,000 antiprotons, we need around about 3 million positrons to then make our antihydrogen. So when we mix it, we make about 50,000 antihydrogen each time. But, and this is a big but, these antihydrogens still have a lot of energy. So we only trap 30 each time we mix these. So we can do this now every 4 minutes. So if we compare this to when Alpha began in 2010, when they were first doing this, they only trapped 1 atom every 2 hours or so. And now we're trapping 30 every 4 minutes. So this is a huge improvement. And this silicon vertex detector means we can detect every single antihydrogen that once we've trapped it and we've manipulated it, we can detect where every single one of these goes, which is hugely important for the work that we do. So that's great. We've made antihydrogen. So what do you do with it? What are you interested in? So what we want to do, and in fact, what the L in alpha stands for, is laser. So one of the things we look at is laser spectroscopy. So we've just got a still from that video. And you can see we've got the bathtub potential. So we've got the antihydrogen trapped inside the center of alpha. And then we've got this purple laser going straight through the middle. So what we want is we want this laser to interact with that antihydrogen. And we want to see what the antihydrogen does. And we want to see if it reacts in the same way that hydrogen does. So this laser that we're looking at here, this is a UV laser. And I think you can probably remember from your chemistry, if you haven't done this recently, that each atom in the periodic table has its own fingerprint. That if you go and look at it in detail, it has its own set of energy levels. And each of these energy levels, you can measure the frequency that's related to them. And once you can measure the frequency of something, you can measure something to very high precision. Frequency is the highest precision that you can measure to for a particular characteristic. So we want to basically take the fingerprint of antihydrogen and compare it to the hydrogen one. So in a tiny bit more detail, if don't worry about the notation here if you've not done your quantum mechanics yet. What we're basically looking at is the ground level of antihydrogen, and we want to excite it up to its first excited level. And that's where our UV laser comes in. So that's our 243 nanometers. And you can see that actually we need 2 photons from that laser to jump up to the first excited state. And then 3 things can happen from this state. It could just decay back down to its ground state. That's fine. We can interact with it again later. It could interact with another 243 photon, and it could be ionized. It could jump up to the continuum. And if that happens, then it's no longer held in that bathtub potential anymore. It will lose its positron, and the antiproton will annihilate on the side of our trap, and we can detect that. So we know if that's happened. What it can also do, it can also mix over to the 2p state. And then it has 2 possible routes it can take. It can decay back down to a trapped ground state, and we can go through the whole thing again. Or it can cause a positron spin flip, and it can end up in an untrapped state, which means again, it annihilates, it hits the side of our trap, we can detect that as well. So what we want to do is we just scan our laser frequency around about where we expect the energy to be for this transition. And we look and see how many of the annihilations that we get, how many of these antihydrogens do we kick out on purpose. And that's the way that we can measure the frequency of this transition. And we can actually, at the moment, we can do this to a precision of 10 to the minus 12, which is already pretty good. However, hydrogen is currently been measured to 10 to the minus 15. So we still have a long way to go to catch up with hydrogen, but that's our aim. We want to be able to measure this transition from this 1s state to this 2s state at the same level of precision that hydrogen is, so we can make a direct comparison. But spectroscopy is not the only thing we do. We do a few other things. We play with microwaves, but the new big experiment that we're looking at now is trying to have a look at gravitational measurements. So if you imagine, for instance, you drop an apple to the earth, you know that it falls with 9.81 meters per second. And this is reasonable. It's been measured, it's been tested. You can do this yourself. Unfortunately, it hasn't been measured for antimatter. No one has taken some antimatter and dropped it to the earth and seen at what speed it goes. In fact, no one's even seen whether it goes down or whether it might go up. So the whole point of our new experiment is to test this out. So job 1 is to see which direction does it fall. Trust me, if it falls up, we're going to take a long time proving that to ourselves before we tell you about it. But then the second point would be, how quickly does it fall? Does it fall at the same rate that normal matter falls? So we have a brand new experiment for this. We can't do this in the sideways trap that I've just shown you. So we built this in 2018, and we're still upgrading this, improving it, working on it. And this is what it really looks like. So remember what we were looking at before. We had our antiprotons coming in from the left, and the catching trap is still there. The atom trap is here, but then boom, there's a massive big new experiment here. So this meant having a new beamline built, and this actually pushes our positron accumulator off the page. So it's now off the screen. But this alpha G is about 3 meters high, and it's inside the center of here that we'll be dropping the antimatter and seeing what happens. So if you'd like to know more about that, you can ask us at the end. But what we're going to do now is Adam's going to take us for a walk around alpha zone itself. So instead of just looking at this, you can see the reality.
Okay, so April's given you an overview of what alpha actually does. I'll give you a look at what it actually is now. So we'll pick up the antiproton beam where we left it, Elena. So Elena is behind this door, and the beam is steered into our experiment. So these are all various diagnostic instruments for us to adjust magnetic fields or to push the particles around as we need. So this is the interface between our experiment and CERN, basically. In this chamber, we have a small foil. This foil is used to moderate the energy of the antiprotons that make it into the rest of our experiment. So we try and control them to trap them. So I'm going to walk you along the reverse side of this experiment. You'll notice some things are missing at the moment. CERN is in the middle of a long shutdown, so we're doing some upgrades. So where April talked about the catching trap, that actually lives connected to this chamber normally. As you can see, it's actually on some rails. So we've currently pushed it out of the way so that we can change the internal structure ready to accept antiprotons at a much lower energy now. The idea being that we're hoping we can catch more and therefore increase our production of antihydrogen. So inside this tin foil, usually we did push in our penning trap. There would also be some magnets you can see here in the background that would steer the beam after that. So let's turn around. We can see some containment vessels for liquid helium. All of our traps are held at 4 Kelvin, so minus 269 degrees Celsius. And this is a box that's used to house our laser system, or one of the laser systems. April's only given a sort of an introduction to the vast array of experiments done by Alpha. So she's talked about one particular laser. So this is where the magic happens. This is our atom trap. It's where the antihydrogen is produced. It's the first place antihydrogen has been trapped and studied. And it's our first real definitive atom versus anti-atom comparison machine. So you can see various windows for laser access. This one is to do a different laser transition in antihydrogen. You can also see these strange looking black boards. They pick up the gamma rays that April talked about as being emitted when antihydrogen annihilates. This is the extension to the beamline that April talked about for the alpha G experiment. This compresses and holds our antiprotons or positrons in that beamline and make sure that they can be moved between the various traps. Now we come to an interesting geometry. This is a special magnet that was designed to send antiprotons and positrons at a 90-degree bend. So it really does just turn them straight at 90 degrees. That is not very easy. And the PhD student from Manchester that designed that was amazing, and it worked first time, first shot. Very impressive. So this is the positron accumulator that April talked about. This is where I started working on my master's, and it's essentially works in the same way as our other traps, where it's a magnet and an electrostatic field. But this time we're relying on nature of it. As everyone knows, radioactive sources are random. They don't give a steady stream of particles. So we have to wait and hold them long enough that we have the correct number to do our anti-hydrogen mixing. So I showed you kind of a walk along what is currently in our zone, and if anyone has any further questions on this, I'm happy to go rogue. It's just the other side of this wall, so I can walk out there with my camera and show people a close-up of various parts of the experiment. But here are some clips from 2018 where we had this this extension of Alpha G. This is our new type of detector made in Triumph in Canada. It works on a vaguely similar premise to the Alpha 2 detection system, but is meant to give us better spatial resolution required for this anti-gravity measurement. Here's me in 2018. This guy is actually my supervisor, even though we look the same age and no one can ever get over that. We are here inserting the first penning trap into Alpha G in 2018. We were rushing to make some measurements before CERN entered its long shutdown, so it's been shut down since the end of 2018 and is due back online the end of this summer. So here you can see we're delicately pushing a stack of aluminium electrodes that are gold plated and electrically isolated using ruby beads. This is a very delicate operation, and I didn't sleep the night before this. That's good. It was a nerve-wracking time, and all working against the clock. We had maybe an hour window to do this, so it was stressful. This is a big photo of the collaboration at the end of the anti-proton run in 2018. I was on night shift the night before this, so I was asleep when this photo was taken, unfortunately. But I was there in spirit, and you can see that Alpha G is kind of a monster of a thing. From the very top to the ground floor, it's about 8 meters. So this is the kind of scale that we're working at. Not quite the Atlas or CMS that April had on display earlier, but still an impressive upgrade. So I'll hand back over to April to give you some insight into how to come to CERN.
Yeah, so if your interest has been piqued by this experiment and by some of the other things we've discussed, how do you actually come and work at a place like CERN? I think it's probably quite an interesting question. So CERN is not just made of physicists, let's make that very clear. There are a lot of people working in IT, engineering, and everyone else that it takes to run such a complex system like this. So if we look at, let me go back up one. On site, on the Marin site where we are, we're on a normal time. We'd have over 17,000 people here. So the site itself has its own restaurants, its own hotel, and all those other things that you might expect for that many people. But what Adam and I are, is we come under users. So we are people who are employed by a university, and then we are sent over to CERN to actually do our work here. So we're not actually employed by CERN itself. But there are people who are employed by CERN, these 2,500 staff members. These people are, along with the fellows and students. And I just put a few things along the left-hand side that you might not be aware of. As I said, it's not just physicists that work here. We need a lot of engineers to make this place work. And CERN even has its own fire brigade. So firefighters from all over the member states can come and work here for a couple of years, gain some experience in some rather unusual situations that you might not normally face back home. So if you're interested in being one of these students, this is a good place to start. So CERN Summer Student Program runs over the summer. It runs from June till around about August time. You need to have done 3 years of your degree before you can apply. But basically what you do is you apply to CERN itself, you fill in all the paperwork, you tell us what you're interested in, you tell us what your skills are. And once you get past the first round, you get put into a very big pool of people. And what we do from our side is we put in a project, and everybody's projects are checked. If the project is good, it gets put forward. And what happens then is that us as project leaders, we get to pick 10 students from the list. And then a very fancy algorithm goes through and tries to match our choice of 10 students to the students that are available and the country quotas for each country, because there are differences between students from member states and non-member states. And we get given a student. So it is not the case that you put in an application and you get cherry picked. Okay, it doesn't work that way. So if you put in an application and you don't get it the first time, it's 100% worth putting in another application the following year, because it might just be that your country quota was full. It might just be that with the skills that you have, there wasn't a project that matched it that year, but there might be one the following year. So don't be disheartened if you don't get in the first time. And what CERN does is they put you up in one of the hostels or the hotels on site, or just the other side of the border in France, and they even give you a living allowance. So this is a great program. You get a couple of weeks of lectures. You get to come and work with us or someone else on one of the experiments, and this kind of experience cannot be understated. Okay, but if you want to come for more than a few weeks,
I think we're running close to the end now. So maybe we focus on alpha opportunities.
Yeah. I'll just skim through these. So if you want to run for more than 3 months, you want to come for say 10 or 12 months, there's a technical student system as well. So you can apply to this. This is useful if you're doing like a sandwich degree or something like this, or the second part of your master's. We also have doctoral students come directly to CERN. This one we don't know so much about, so you'd have to put your questions to CERN. But what we can say is these are all of the people who work with Alpha. So we have all of these different institutions across the world. In particular, Manchester is looking for a PhD student right now. So if you're interested in working with Alpha, you can message Will and he'll give you some more information. This is for a UK-based student. If that doesn't apply to you, you're not a UK student, you can apply to any of these Canadian institutes. They're always looking for good students. And the person you would contact is down here at the bottom. This is Makoto. You can send him an email and he'll give you some more information. If you happen to be stopping by and you already have a PhD on the random off chance, we also have 2 postdocs going. Again, this is with the Triumph in Canada. So go and have a look at these links and see the kind of jobs that we have here. And finally, don't forget this, right? You see a talk like this, you see people who work at CERN and you think, oh my God, that can't be me. It's not possible. I'm not good enough. But what you're seeing is the tip of the iceberg. You're seeing the success, the bits everybody wants to share with you, and you're forgetting the rest of this. And this includes people who didn't get in the first time to something they applied to, who didn't get the PhD the year they wanted it to. Everyone goes through this. I see in the chat, you're missing procrastination. Yes, that would be another good thing to add on the bottom corner of this one. I agree. So don't think that you can't be one of these students. you 100% can. So I think what we'll do is we'll finish here and ask if you have any questions you'd like to put to us.
Great, thank you so much. That was very interesting and a great way to kick off the morning. So I've been keeping an eye on the chat, and so has Joe. So I'm going to hand over to Joe, who will be reading out some of the questions. I think the first question, just to get us started, was is the region on the interior of the ring still utilized for regular agricultural purposes? So,
Oh, okay. On
The
LHC.
LHC.
Yes, yeah. There's plenty of farming around, and actually the grass is cut at CERN by our own CERN sheep that normally live in France and then come over here once a year to trim the grass for us. So yes, that's true.
The scale of the LHC is such that there's a whole town inside the circumference, right? It's, I live in the middle, so
Surrounded by your work. Very appropriate.
PhD life.
So the next question that we had came from Tomas, which was, how likely is it that tunneling effects from the bathtub potential cause losses of anti-hydrogen atoms?
So we don't see any losses once we have the bathtub potential there, and we have the anti-hydrogen atoms in there that have less energy than that potential. Once that's the case, what we can actually do is I said we get that shot every 4 minutes, and what we can do is hold on to those anti-hydrogen atoms we made in the first shot, put them to one side of our trap, and get in the next shot and make another lot, and then add them to the first set, and we call that stacking. So what we can actually do is we can build up to over 1,000 anti-hydrogen atoms in about 8 hours.
Excellent. Andrew Smalley then asked, what are some of the potential future applications of greater understanding of anti-hydrogen?
Oh, interesting. That could
Sort of
be big.
speculation. That'd be interesting.
That's a tricky one. I mean, it's worth remembering that we're talking on the scale of thousands of atoms when we think of 12 grams of carbon is 10 to the 23 atoms. The scale that we're working at is so far away from something macroscopic we can imagine using in everyday life. It's hard to picture where that could come in. But not a bomb. We'll hold our hands up to that one.
Yeah, most of the application is going to be in improving theory. So if we can if we find any kind of difference between anti-hydrogen and hydrogen, we can adjust the theories. We can know which way we want to go, because we know the standard model is not perfect. We know it has problems, but it is very, very good. So you don't want to throw it away. You just want to tweak it and improve it.
Next question came from Alid Horner, which was, how much loss do you have from the flying out along the beamline instead of radially through the detectors?
I guess he's talking about the LHC there. But
No, I think it's like the bathtub potential. So the way that this works is that imagine the anti-hydrogen is bouncing back and forth along that bathtub potential. It's held radially. Well, we turn off the magnet that holds it radially, so it shoots out the sides. So we don't have losses heading down the beamline that we can't see. I think that's
yeah, we intentionally block either end, so we don't lose anything there.
The next question came from Freya Woods, which is, what is the expected outcome of Alpha G? Are there alternate theories suggesting acceleration due to gravity, which is different for them?
There are many alternate theories, and this is part of the problem, right? Gravity is that force that just does not want to sit well and play well with the others. So if we could find something interesting to investigate here, if we find something that's just even a tiny bit different, it could try and help narrow down those alternate theories to things that are worth investigating further.
What's your current preference? What is the is there like a consensus at CERN for what the most viable theory for these things are currently, or are all held with a kind of certain level of respect?
Those that might imply that it goes the opposite way to normal matter are going to be more easy to rule out with the first experiments with alpha G. So those ones, if they are wrong, will be quicker to dismiss. But then the others, it's much more tricky.
Then we have some slightly more personal questions, which are: if you could identify one thing that you did or you experienced at university that contributed most to your reaching the position you're currently at, what would that be?
Adam, do you want to go with that one?
That's a tricky question. I think experiencing working in offices and doing other jobs that supported me through my degree, I think realizing that I got bored quite quickly doing those jobs pushed me to apply for everything and to find my way onto the MPhys program at Swansea, which then I was lucky enough to get my project selected here, and once I was here, I managed to meet my current PhD supervisor. But I think it's about finding the right topic that you're passionate about, and really being able to enjoy your PhD, because it is a slog, it is a grind, and if you don't really love the physics that you're doing, it's kind of difficult.
Fantastic. Okay. The next question came from Alexander Lewis, which is for the alpha G experiment, how do you know where the anti-hydrogen atoms are initially, and how do you account for their initial velocities?
Okay, that's a great question. So what we have within alpha G is Adam showed you one penning trap, but we have multiple penning traps that span that whole distance, because that's a really long distance. So what we can do is we can apply our potentials, and we know where those potentials are, and we can position them where we want them to be with quite accuracy. But what's even the more important part of that is the detector that sits just outside of those trap electrodes is really precise. So we didn't have a slide in this one, but we do have some data where you can literally line up the penning trap electrode that they were sitting in, where the potential well was, with exactly where the detector said it was. And basically what we did was we had an evening where one person put the particles where we wanted them to be, and another person running the detector had to guess where they thought we'd put them based on what the detector was saying, and they got it right. It was perfect. So it's the accuracy of the detector that's really important there.
Okay.
Jump in, and there's a question slightly earlier in the chat from James that says, do you envisage cooling and amassing a liquid phase of antihydrogen in the near future?
Adam, I think it's your turn.
Yeah. Notice the questions I'm being given. Again, we're in a regime at the moment where you can treat our experiment essentially as an ideal gas, where there's no interaction between the atoms, because you're imagining a volume macroscopically like this size, right? A few centimeters radius, and you've only got tens, thousands of atoms. So you're working in a volume that these particles aren't interacting. To cool them and bring them into a liquid phase is even one step further. The first thing you'd be looking at was some kind of condensate, but yeah, I think we're still a long way off something like that.
Fabulous.
Question from Freya Woods, which was, it was mentioned that you use microwaves in your experiments in addition to the other aspects. What effects are these being used to study?
Oh, that's definitely a Adam question. That's part of his PhD.
Yeah, so there are a few different applications. I'm using them at the moment to drive different frequencies of electron motion in our trap, because those frequencies are dependent on the magnetic field. By understanding the frequency, we can extract the magnetic field. This is super important for us to be able to understand the trajectory of the antihydrogen for our gravity experiments. It's also for anyone in the audience who knows anything about spectroscopy. All of these things ideally will be done at zero magnetic field, but because of the way we need to trap antihydrogen, that's not possible. So we need a good way to characterize our magnetic field to make sure that we understand the frequency dependence there. Also, we can drive microwave transitions. So in the same way that we can use lasers to excite the antihydrogen, we can use microwaves to excite them as well. This is a common detection method for us. If we have trapped antihydrogen, we can fire in a microwave of a certain wavelength, and that antihydrogen is ejected from our trap. We can definitively say it's there. So hopefully that answers your question. Thank you.
Thank you. Next question came from Robert Lumpkin, which was that obviously calibration is an important part of the experimental design at CERN, but how do you calibrate a particle accelerator?
How do you calibrate a particle accelerator? That's
great difficulty.
Yes, that is difficult.
There's a whole department at CERN that's based on beam instrumentation. So they take very precise measurements of everything to do with the LHC. Everything is controlled to a level that blows my mind.
Yeah, I think maybe an interesting application is, so the tunnel itself is actually affected by the tidal forces of the moon. So they have to constantly just adjust the proton beams as they go around the LHC. To do that, they put detectors in and out of the beam. So they check it. And I think this happened when one person was on shift in the data center, and they kept seeing the beam disappearing all the time, and they were like, what is going on? And they said, well, actually it's because it's full moon and we need to do this more often. So yeah, they slide detectors in and out.
Okay. The next question comes from, oh goodness me, it has Scandinavian characters, so I'm not going to attempt to pronounce that name, unfortunately. The question is: are there currently any experiments at CERN which are looking for dark matter?
Yes.
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 There are a number. I mentioned the base collaboration in this very building. They've put some constraints on possible dark matter sources based on the fact that they have a very precise measurement of a single particle. So they say that if there was dark matter in this region, they'd see it. So they've discounted that. There are also several other experiments dotted around that make dark matter claims. I'm not sure if April has any details on that.
No, not off the top of my head. It's an interesting topic that a lot of experiments seem to dabble a little bit, but it's not their main focus, I would say.
Thank you. Okay.
Fabulous. Well, we have time for one more question if anyone wants to sneak one in real quick. But if not, we'll wrap that up here. Thank you guys so much for joining us again. It was a really interesting and a great start to the last day of Planks. Yeah, so now we're going to take a 15-minute break before we have our talk from Professor Jim Al-Khalili at 12. So see you all back here in 15 minutes. Thank you again to our lovely speakers.
Right, thank you.
Thank you.
Thank you very much.